Lesson 15. Attributes and the ISQ Library. Welcome back to the SysML v2 Deep Dive series. Last time, we used multiplicity to say how many parts a system can have. 4 wheels, perhaps 1 driver, perhaps no driver at all. That tells us how a system is assembled. This lesson gives those parts physical properties that mean something to a tool. We are talking about attributes, quantities, units, and dimensional analysis. In short, we are making it much harder for a model to say something physically absurd. Let's start with why units became a modeling problem in the first place. On September 23, 1999, the Mars Climate Orbiter fired its engine to enter orbit. It came in about 170 kilometers lower than planned, broke apart in the Martian atmosphere, and was lost. The failure was not exotic. One team supplied impulse data in pound-force seconds. The software receiving it expected Newton seconds. Each team had valid numbers. The system did not carry the units needed to tell the difference. SysML v1 had a sophisticated answer to this problem. QUDV for quantities, units, dimensions, and values. You could build value types, map them to quantity kinds and units, then use parametric constraints to catch invalid equations. That capability was real, but the usability was immense. Because the underlying UML type system was blind to physics, it had nothing useful to verify. Units became documentation, not engineering. The change in v2 is simple. Give each value a physical meaning the tool can check. SysML v2 replaces the v1 value property with an attribute usage. It also includes a standard quantities and units domain library built on the International System of Quantities, or ISQ, and the SI system. An attribute def defines a data type, and an attribute is the feature of a part or occurrence that relates it to a concrete value. The ISQ and SI libraries supply the supported quantity kinds and units. We will separate those ideas carefully after the example. Here is a spacecraft model where mass and power cannot be mistaken for each other. Feel free to follow along with a free account on SysModeler.ai. Let's walk through it. The two imports bring the standard quantity kinds and SI units into the package. That is what makes MassValue, PowerValue, kg, g, and w available by name. Dry mass has the type MassValue with an initial value of 1500 kilograms. The important word here is not 1500, it is MassValue. Payload mass is also a MassValue, but its value is written in grams. 500,000 grams and 500 kilograms represent the same physical dimension. A conforming tool can resolve the conversion when it evaluates the mass rollup. Total mass and max power make the distinction clear. One represents mass, the other represents power. They are not interchangeable numbers. The mass rollup assertion says total mass must equal dry mass plus payload mass. Power floor says maximum power must say greater than 0 watts. We will return to why assert constraint matters in a moment. Now consider this relationship. This is invalid. Dry mass is a mass value. Max power is a power value. Adding them does not type check. That is the Mars Climate Orbiter mistake caught while someone is editing the model, rather than after a spacecraft reaches Mars. 3 details make this pattern reliable in a real model. First, separate the type of a value from the standard quantity it represents. MassValue is an attribute definition. It defines the type of a mass value, including its magnitude and measurement reference. ISQ mass is a standard quantity usage. It represents the ISQ notion of mass. Most of the time, type your attribute with the value type. When the downstream analysis or a library constraint needs the explicit ISQ quantity, subset the quantity kind instead. Either convention can work. Pick one for the project and apply it consistently. A model that randomly mixes quantity kinds and value types makes people wonder whether the distinction was intentional. Second, decide whether you are describing a relationship or requiring it to hold. A bare constraint declares a conditional relationship. It may evaluate to true or false for the values bound to it. An assert constraint, or simply assert, makes that relationship an invariant. If it evaluates to false, the model is inconsistent. and a SysML v2 tool can flag the violation. So this is a description, and this is a commitment. If you expect an invalid mass calculation to trigger a validation failure, use the assertion. Third, treat the unit in square brackets as part of the value, not as a note beside it. In 1500 square brackets kg, the square brackets are not a comment, and they are not a label for a human reader. They form a measurement expression. The number and the model reference to kg become one quantity value. That is why 1500 kilograms and 500,000 grams can participate in the same calculation. The library defines how their scales relate, so the tool can normalize them as needed. Here is the practical change for engineers moving from SysML v1. In SysML v1, a value property becomes an attribute usage in SysML v2. In v1, teams often bypassed the full QUDV library and built lightweight local types. In v2, ISQ and SI provide standard quantity kinds and units as part of the language library. Where a v1 value could ultimately behave like an undifferentiated real number, v2 uses distinct, dimensionally anchored types such as MassValue and PowerValue. Where v1 often placed a unit in a tagged value or a comment, v2 makes units part of the measurement expression itself. Where v1 equations often had to calculate unit conversions manually, in v2, the standard library can resolve compatible scales such as grams and kilograms. Where v1 required a parametric diagram to map properties to a constraint block, v2 can place an assert constraint directly inside the part definition. And where dimensional errors in v1 might survive peer review, physical testing, or worse, a conforming v2 tool can identify a dimensional type mismatch while the model is being edited. If you take one idea away, take this one. SysML v2 treats MassValue as a real physical type, not a number with a comment beside it. Try to add power to mass, and a conforming tool can warn you. The model is no longer a structural description. It can check whether its equations make physical sense. Your model can now tell mass from power and carry units through its calculations. But accurate values are only half the picture. Next, we ask who actually owns the hardware, part or ref part. That one choice decides whether a shared power unit appears once in your mass rollup or gets counted twice. See you there.